Hey, thanks everybody for joining us today for our GoAERO expert lecture. As you know, we're so pleased and so proud to have our sponsors and our partners engaged with us, including Boeing, NASA, RTX, and so many others, including over 30 organizational partners from around the world who are supporting the GoAERO Prize. And today, we're incredibly excited to have Kristina Menton, head of flight from Pivotal, here with us today. Kristina is a core member of the Pivotal team, where she spent nearly a decade leading flight testing, pilot training, regulatory affairs, and customer success. Prior to her tenure at Pivotal, Kristina worked in R&D at Pratt & Whitney and GE Power. Recognized for her impact at the intersection of emerging technology and operations, Kristina was named one of the Globe and Mail's top Canadian changemakers in 2022. She is a passionate aviator, a licensed private pilot, and an experienced eVTOL pilot. Outside of work, Kristina is an avid snowboarder, kite surfer, and cyclist, and shares her adventures with her beach-loving dog, Maple. She holds a bachelor's degree in mechanical engineering, summa cum laude, from the University of Toronto, and was a fellow in the Leaders of Global Operations program at MIT Sloan. We're so pleased to have Kristina here today. Thank you so much for joining us.
It's great to be here. Thank you for having me. So I'm excited to be here with everyone. I'm going to get my presentation up and then we can get started. So I'm here today to talk about Sim to Sky, engineering safer eVTOLs for the GoAERO lecture series. And why I think this is important is because GoAERO has a lot in common with Pivotal. We're looking to change the future of aviation. We are looking to advance we're looking to take new types of technologies into the skies to be able to support the future of aviation, whether that's bringing it to people in need, providing services where they need them, and using these applications to really help the world in a new way. So what I understand of the GoAERO's mission is that everyone in this group is looking to design the world's first compact autonomy-enabled rescued aircraft that are simple and safe to fly. We're doing the same at Pivotal. Our mission is to create easy, safe, and fun vehicles that fall within the Part 103 category. This is a flight that we did around the Golden Gate Bridge here in San Francisco, July 4th of last year. And it really marked a key point for the company that we were integrating into traditional aviation spaces. We got a huge amount of public view, and it was an incredibly fun flight to fly. This is one of our pilots who's flying here, took off from Sausalito, flew up and down the Golden Gate Bridge, abided by all existing regulatory frameworks within government and FAA, the local government and FAA. And it really marked, hey, we're out there and we're doing this. But one thing that I'd really like to talk to this group about today is that this didn't just happen overnight. And as you go through challenges and development and research on different types of technologies and different types of aviation applications, you have to have this in mind, the total mission in mind, but you have to start small. And the way that we work today is design by requirements, for me, as full systems analysis of the vehicle. Now, when you're getting started and you're a small team and you're building technology, that's not always feasible. You can't afford a $200,000 software package to validate an airframe that maybe you'll fly once or twice. So making the right trade-offs is something that I'm going to talk about in the presentation today, and how those trade-offs can trigger safety and reliability towards the end product. So where we started here, previously called Opener, now called Pivotal, is the Part 103 category. It's like, let's look at a framework that exists today. Let's find an area where we can legally fly aircraft today to be able to start the technology. Because if we're required to change the regulations and work with governments and create a new category, we're going to have a lot more funding. And what we know in 2014, when we first moved down here to California, was, we have an idea. We don't have a product. We don't have a completed design. We have a huge amount of invention in front of us. So what we did with Opener is we took the idea of Part 1 of 3 category. So in Part 1 of 3, it's an existing FAA category. Many of you are probably already familiar with it. The aircraft must weigh less than 254 pounds, plus amphibious systems and safety systems. It must fly less than 55 knots, so pretty slow in power level flight. It must have a stall speed that does not exceed 24 knots, calibrated airspeed. They're designed for a single occupant. So you'll see in both of these images, just a single occupant on board. And it must be operated with visual reference with the surface, meaning the pilot must be able to see the ground. So it must have some kind of cockpit where the pilot can see the ground. There are also operations requirements in terms of how you can fly the aircraft. So you must fly in VFR, you must fly over class Gulf airspace, over uncongested areas. You can fly in class Delta or Echo with approval. And so we took this category and we said, okay, the left-hand side is the aircraft that exists in this category in 2011, 2012, the early 2014. And the right-hand side is the Opener black fly aircraft. This is the version 2 and the first version that we put people in here in California. And we said, hey, these aircraft are going to look very different, but they can actually abide by the same current regulations. With our mission, we knew that we wanted to create something that was going to change the world, but also be safe. So the left-hand side aircraft, not very redundant. It has a single propulsion system and many different opportunities for failure. The right-hand side is designed to be triple modular redundant. So what that means in terms of triple modular redundancy is that you don't just have one system, you don't just have 2 systems, but you have 3. So that allows you to bound the known good sensor data within a bound, but then also to compare across 3. If you're just comparing 2, you don't really have all the time enough information to be able to say which one is the most accurate. But TMR, triple modular redundancy, allows you to have 3. When you have 3, the 2 that are correlating higher, along with a lot of different algorithms, can say, okay, what should the flight controllers be using to be able to operate? The left-hand side vehicle does not have flight controllers. It's completely mechanically focused from the pilot, whereas the right-hand side is all fly-by-wire. So due to the technology advancements in propulsion, particularly with motor design, battery design, and flight controllers, so IMU technology, inertial measurement units, we're able to create a very complicated system that has flight controllers to be able to understand that system and correlate which way is up, which way is forward, which way does the pilot want to fly. The aircraft that it's Marcus who's flying it, our founder, had a single joystick at the time. If it has a single joystick, you need to know that joystick is triple modular redundant, because if anything fails, or at least dual redundant, if that joystick fails, you need to have a way to be able to get to the ground. So that was something that we built into the really fundamentals of the company. And as we started this technology, we weren't looking at that end product that was going to be flying around San Francisco. We were looking at, okay, how can we prove that we can have triple modular redundancy? Because we're not going to put a person on board until we can prove that there's a system in place to back up every one of these other systems that we can fit within 254 pounds, plus amphibious systems and safety systems. This is something that no other company had ever done before. And so we needed to invent technology, including propulsion design. We designed our own state estimators and a lot of other technology to be able to prove, can we make this system package small enough to legally fit within Part 1 of 3? So at that time in 2014, there was a huge amount of development that had to happen to even prove that this was feasible. We worked iteratively on the most challenging problems. So propulsion design. If you weren't able to get enough lift, can't even hover. We need to make sure that we can get enough lift to hover for at least 2 minutes at the time was the milestone and objective. And then with an aircraft as simple and light as the pivotal Blackfly V2 there, you need to know that the propulsion systems can't articulate. To be able to articulate, you'd add an enormous amount of weight and complexity. So everything must be fixed. And that's what triggered the tilt airframe design that Pivotal has been pursuing since 2011, when Marcus took the first flight in Coburg, Canada. So that means that the propulsion systems are fixed to the wings fixed to the fuselage, and the whole aircraft tilts. When I joined the company in 2015, there were lots of questions from advisors and research scientists and people who joined the company about, well, why is there no landing gear? Why are there no wheels? You should add landing gear and wheels. And ultimately, that's because we chose Part 103. Part 103 is 254 pounds, and any amount of weight that we add to the vehicle would contribute to increased drag, which is not desirable because that would decrease your range, but it also increases the weight and potentially makes the aircraft not viable. So a huge amount of research development went into that landing system that is autonomous for the first 10 feet of takeoff and 10 feet of landing every time, because you don't have a landing gear there. You need to know that it's going to be soft and that it's going to be controlled every time. So really focusing on, okay, what are we trying to achieve? What are the regulations around us? And how do we make sure that we are focused on solving that problem? And the aircraft might not be as beautiful as we want the end product to be. It might not be as aerodynamically efficient as you can see, but it's something that we can manufacture pretty easily here in Palo Alto. And it was something that we could design the triple modular redundant architecture in place of. Now, I think a lot of people on this call will be able to identify with the video like this. So things didn't start in a giant factory. Things started in tents. They started out in the field, really understanding the technology that we had and ensuring that that technology was viable for the future. So that meant a lot of iterative design. That meant a lot of breaking things, but making sure that we had test plans and test teams and roles and responsibilities within the core group to be able to ensure that every time we went out to fly, it would be testing something that we wanted to test. So inevitably, there are going to be things that you learn along the way that were not part of the test plan, but you want to mitigate those as much as possible. So being part of something like the Flight Test Safety Council, going to lectures by other companies where they describe their test framework, where that framework is using hazard and risk analysis, is you need to understand what you know, and then you need to understand that there's things that you don't know, and everything that you do know needs to be part of that test plan, so that you have the mitigations in place to understand, okay, are we choosing the right time to put this aircraft in the skies? Because that's one of the hardest decisions that you will make as an new aircraft design manufacturer, is when will you be ready for that first flight? When will you be ready for the first high power run of a vehicle? Because that is an enormous amount of energy that you'll be providing to the system. And you want to know that you're testing the things that you wanted to test, and you're not potentially compromising the vehicle you've worked so tirelessly to be able to create. We do that through a number of meetings here at Pivotal. One is through a very rigorous safety review board process. So the safety review board here at Pivotal has existed for the last 10 years. That brings in subject matter experts from the company and advisors external to the company, including test pilots, NASA astronauts, professors, military, civilian advisors, to come in and really vet, okay, how do we make sure that Pivotal is making the right choices, is asking the right questions, and is using industry best practices wherever possible. So having something in place like a safety review board, whether it's meeting monthly or weekly or quarterly, depending on the needs of the company at the time, was a way that we were able to really ensure that we were bringing best practices into a very small team, which I'm sure many of the teams here at GoAERO are. Figuring out how to understand the risks, question the time pressure, question the schedule pressure. There's going to be all of these external factors that are saying, okay, we've got it, let's just fly, it'll probably be okay. Or, we need to get to X milestone, so these are the risks that we're willing to take. And that might be, we're going to run the propulsion system up to full power because it's passed every test so far. And we need to be able to say, okay, where does it actually break? And so that's part of a test plan that has a structured hazard risk analysis that will say, this is how we're stepping up to mitigate risk. And then at some point, we're going to have to take that risk. And if that risk, that hazard does happen, then this is how we're going to have the emergency response available. Making sure there's briefings before tests, briefings after tests, debriefs, and structured analysis of who's responsible for what was a really big part of the company, even way back when we were operating out of tents and in fields. The tent that you saw was actually a test operation site that we used up in northern Canada, where we operated for more than 20,000 flight miles with the Blackfly V2 aircraft. Now, another thing that we've had since the very beginning of the organization is a focus on data. So, this is one of the key words that everybody's using in interviews, in the news, everything today is data and AI. And how do you make sure that as you're building these aircraft and you're running through these test plans, you have a structured analysis of what's the information coming from the vehicle? What state of health is the system? And how can you leverage these pieces of data now for the future? So what you're seeing is the a data visualization dashboard that we have. It takes all the data from the vehicle and puts it in a way that's very easy for engineers to be able to see, analyze, and investigate. This is very similar to the system that we had in place in 2014. We came down here in California. And we built an internal system, which we call Dash, which allows the vehicle to upload all of its data to the cloud and then be able to post-process that data. One of the first things that we did was, how do we get the information to the engineers faster? How do we get the right bounds on the data so that we can, through an automated system, run checks and balances and reports on vehicles, flight miles, and even subsystems to be able to say, is that system operating the way that it should? And that really triggers back to what I was saying with the hazard and risk analysis is, you need to know what you don't know, and you need to know what you know. So if you're having all this data come in, it's a huge manual process to be able to confirm that that data is in fact correct. And seeing any degradation in the system, it needs to be an automated process. And there are a lot of AI tools and data analysis tools, which are able to make this much, much easier today than it was in 2014. The data that we're capturing from the vehicle, you can see the connection status so that all of the sensors are connected through TMR logic, so triple modular redundant connection. We have the aircraft mode, so the aircraft transitions from a landing mode to a hover mode to a cruise mode, and at all times, the PIC, the pilot in command, needs to know what mode that aircraft is in. Because if there is mode confusion, that's when controls are no longer intuitive because you don't know what mode you're in. So it's important that the pilot both sees critical information when flying, whether that pilot is flying as an RPIC remotely or on board the aircraft. And then also all that data is going up to the cloud to be post-processed to say, should we proceed with the next flight? This also allows companies who are building technology to be able to see how the technology changes over time. So whether that's efficiency, whether that's reliability, whether that's triggering preventative maintenance in the future, this allows a huge amount of ease and really prevents some potential failures with the aircraft design, and also allows you to correlate between different types of aircraft, how the aircraft are performing. Another way that we make the aircraft safer is through the whole journey of what a mission looks like. So this is a nice visualization which shows when you have a mission, whether that is to deliver goods to someone in need, whether that is to bring a paramedic somewhere, or whether that is to simply just go for a flight. If you're flying as an RPIC remotely, flying a drone, or if you're in the cockpit flying a traditional fixed wing airplane, this is something that is across the board required for any mission. So at first you need to know what the mission is. You need to plan that mission. So that would be looking at airspace. That would be looking at the environmental conditions. What's the weather doing? What's the meteorology? What's the distance you want to fly? Can that aircraft do that distance at that density altitude? That's something that's traditional within standard aviation, and we require all of our pilots to go through ground training specifically on how to flight plan, how to understand the system and the aircraft, and how the capacity will change over the course of your flight, how the motor performance will change over the course of your flight. In addition to that training, we also require all of our pilots to go through FAA ground school so that they understand airspace, meteorology, and traditional flight planning, like a traditional fixed wing or rotorcraft, because ultimately we want all of these vehicles to be able to integrate with traditional aviation. I get asked the question all the time of, well, what would it look like if there's drones and these types of vehicles in the sky all over the place? And, it could look a lot of different ways in the future. And it's up to us to ensure that we have the training in place and we have the cooperation in place to be able to integrate seamlessly with the skies. So far, we've had no issues with neighbors because we communicate with the neighbors. We make sure the aircraft takeoff and landing is quiet. It's less than a leaf blower in terms of noise, and it only takes about 5 seconds for it to be able to take off. So it's a very short period of time. So making sure that we are flight planning and integrating with other traffic and considering the environment that we're going to take off from, whether that's an airport or a backyard, making sure that that is part of the training for every single pilot so that we can integrate seamlessly into the environment. Then next you have to assemble the aircraft. The pivotal black fly aircraft and helix aircraft come in 3 parts, the fuselage and 2 wings, and they can be assembled in about 30 minutes with 2 people. So making sure that the aircraft is airworthy and is able to be assembled. So for missions where the aircraft is not always taking off and landing from the same place and where potentially the duration of flight, in this case 20 minutes, 20 miles, is shorter, you need to have the ability to rapidly deploy. So to be able to move the aircraft around, be able to assemble and disassemble. Next are the pre-flight checks. So the aircraft needs to know it's been assembled if it's working properly, if everything in the system is connected, and if everything is ready for flight. That's really important, and it's not something that any other Part 103 aircraft typically did. Traditional aircraft will go through a run-up procedure where you basically take the aircraft up to a run-up area and you'll go through a set of run-up procedures to confirm that the magnetos are working and that the engine flap and all the control systems are in place. But now we can move that to built-in systems for systems that are simplified, like the ones that we're building today. So with simplified flight controls, there's a huge amount of data that's coming in from each one of these sensors and systems. And so a lot of those pre-flight checks can be automated. That makes them more objective and also gives a secondary because we want the human operator to be doing a visual inspection as well. So it adds another layer of safety. Next is the actual flight, which is for me the fun part, which I'll talk about a little bit later. And then after that, the post-flight data. So making sure that that data is uploaded in an expedient way to a cloud, post-processed, and that the system is performing as it should, whether that's mission success or whether the mission had to be aborted for whatever reason. That trickles into a system for continuous improvement, so continuous improvement loop, which goes back to, okay, if we had to abort the mission due to capacity, how do we adjust our flight planning to ensure that the next time that we will be able to plan appropriately? Did we not have enough charge or daylight hours, et cetera, to be able to complete the mission? Or did we? And therefore, the flight planning was successful. And then it all comes back to training. So training's at the end of the line here, but it's also at the beginning. I mentioned flight planning, and before you even get into the cockpit, there's a huge amount of training. And there's also training after to take all of the continuous learnings from vehicles integrating with airspace and training new pilots to be able to ensure that the system is getting better and better over time. So here you can see a visualization of the flight planner that Pivotal's designed. This flight planner takes into account battery capacity, density, altitude, environmental conditions, and wind conditions to be able to say, okay, how much further are you allowed to fly? So when we first designed the vehicle, this was completely done in Excel. It's how far can you fly? What's the density, altitude? How long are you in cruise? How long are you in hover? How do you get the performance metrics of the aircraft into data? And then over time, we've been able to move that out of Excel and into a really nice app so that every pilot can plot their route and be able to have a sanity check over, okay, if the winds are much higher than I expected, how would that affect my flight? And through an iterative process, can go through the planning more quickly and more easily. And then also visualization really helps to make it more friendly to a lot of different pilots. This app will also show things like approval permits and TFRs and airspace, because that's something that it is really important as we integrate into the skies, that we are ensuring that we're abiding by all the regulations that are in place. So next is assembly. So this video shows the assembly of a Blackfly aircraft, similar to a Helix aircraft. It fits in a trailer. It needs to be rapidly deployable, as I said earlier, and it needs to be able to have all of the systems around it. So 2014 through 2018, we were focused on building the technology, solving the challenges that were ahead in terms of how do we invent an aircraft that's going to be able to fit in this category, and can it be safe enough for humans to fly? After that, it became, how can you assemble it really quickly? How can you move it around between places? How can you make it so that it is user friendly and has the human machine interaction focus to be able to be a solution that's solving the problem that you're looking to solve? Next, this is a visualization of the pre-flight checks. So as you start building the design, the pre-flight checks are typically quite manual. You might have to program into an aircraft, download all the logs, and be able to see how is this system performing. With a lot of the tools that are available today, it's quite easy to have that be Wi-Fi connected and have an automated system of checks. So this is an app that we've created that takes in the data, uses a connection directly with the aircraft. So it doesn't need to go to the cloud first. It goes directly to the aircraft and is able to walk that pilot through that pre-flight check. So it checks the pitot tubes, it makes sure that they're undamaged, secure, the GPS antennas are all secure, that every position of the joystick is recorded through the flight controllers of both joysticks. We have two for redundancy to ensure that not only does it help for left and right-handed pilots, but also it allows redundancy. If a button were to get stuck or a joystick weren't responding for whatever reason, you could switch to the other joystick in flight and still be able to land. It goes through the seat, the restraints, everything that the pilot needs to do. This is similar to a kneeboard check that a traditional aviator would be familiar with. And then it checks the built-in systems. So it runs current through the different motor systems and says, hey, is the back EMF of this motor consistent with what I expected to see? And if not, then maybe you shouldn't fly. And so the aircraft will actually be grounded if you can't get through all of the different pre-flight checks until that check is able to pass. It goes through some human checks as well to make sure that the pilot is ready to fly, that they've passed the I'm safe checklist, and that they meet the requirements to be able to fly. They also confirm that the airspace and approvals to fly are within the regulatory allowance of Part 103, and check the aircraft by doing a final walk around. So really focusing on what is traditional aviation, what is the best known true, and how can we add technology to that to make it easier for pilots to do effectively, easier to get right, easier to be able to report back to the pilot how the system is operating, and not require the pilot to hear something slightly different and be able to say, is that normal? Is that within the balance of normal, or is that outside the balance of normal? How do we make these subjective decisions objective wherever possible? And then you get to the flight, which is the most exciting part of the whole day, whether that's flying an RPIC, so a remote aircraft up in northern Saskatchewan over fields of canola, or that's jumping in the cockpit and flying from Sausalito over to San Francisco. It is one of the most incredible things that a human can ever do. Getting in the cockpit and flying an aircraft, being in control of something that's in the sky, having that unity with the flight controls to be able to say, I want to bank right, I'm just going to push the joystick to the right. The aircraft does a coordinated turn. It changes the differential thrust of the 8 different propulsion systems and the 8 different control surfaces to be able to do a smooth, controlled turn. It compensates for wind. It has an incredible flight deck, which is communicating in a simplified way to the pilot the information that's coming to the vehicle and the information of the surroundings. Typically, when I fly, I'm only looking at the map if I'm really trying to see how well did I do that pattern. Otherwise, I'm looking out the cockpit. So you've got more than a 180-degree view of your surroundings, which makes it easy to be able to fly by visual. And then you have communications in your headset from the view screen of your altitude or any potential warnings. Critical information we put on the left-hand side, because that's kind of where the pilot is mostly looking. And we include things like battery, motor temperatures, your ground speed, and your pitch. So that contributes to which mode the aircraft is in. Other important information like warnings would also pop up on this. So if the system were to be degraded, whether that's a avionics system or a GPS failure, those things don't typically happen in flight, but we train every one of our pilots to be able to react if they do. And that makes them safer in the aircraft when they do fly. So this here is San Francisco. The aircraft also is able to operate in over water and in mountainous terrains where there aren't that many roads. So how can we use aircraft like this to be able to get from one place to another where there isn't traditional roads or the roads are quite far apart, bridges are far apart, to be able to make a more expedient way to get somewhere. Or just instead of having to hike 15 hours to get to a ridge top, you can go fly there. You can see the view and you can fly back. So there are a lot of different applications, even within the short duration of 20 minutes, 20 miles. The aircraft that you see here, the pivotal Blackfly V3, it's an extremely robust design. And really that's from a decade of rigorous test and proven technology. So flying over 8,200 flights, 46,000 total miles, more than any other company in the eVTOL space that we're aware of, with 1,600 crewed flights so far, and no reportable incidents. So the aircraft is extremely reliable and robust, and that really comes from the focus that was put in 2014, 2015, 2016 to make sure that the aircraft is being designed for reliability, designed for redundancy, and designed for safety. That we have all of that data that's been coming in from each one of the airframes we've built since then, correlating that data with reliability metrics and making sure that it is built to be robust and proven, because it's important that we avoid incidents. We don't want to, an incident in this space affects everyone in space. And it's important that wherever possible, we want to be designing the aircraft, training the pilots, and building the ecosystem around these new types of aircraft, these new types of simplified flight controls to be able to keep airframe, people, and property safe. Then after the aircraft flies, we also use the app to do the post-flight checks. This is an incredible way to walk through the flight. So you get to go see how many flights you've done, the distance of every flight, go through the map. If there were any warnings, it allows you to relive what that experience was in the air for your flight. A lot of our pilots will use it as something similar to Strava, and they'll share it with their friend. They'll try to do the flight again. They'll try to improve their metrics. But it also helps to say, oh, like, how much battery capacity did I use over time? And how was my flight planning? Did I follow the route that I had designed, or did I take a shorter route or take a longer route? So these different pieces of feedback allow our pilots to not only share in a social way, track their stats and performance, but also improve their ability to fly over time. So that's not something that traditional aviation really has. When I go out and fly a Cessna, I don't get a report at the end of that flight that says, oh, how did I fly compared to my briefing? And that's something that we think is enormously valuable. This allows not only the manufacturer to be able to design the aircraft to be able to perform up to consistent specifications and limits each time, but it also helps the pilot to say, did I brief exactly what I executed? And what did I execute that time? And how would I change it next time to be improved? And we think that's an extremely robust and valuable tool. Also, if there were any alerts or warnings, you'll see the yellow warnings on the screen here. Similar to traditional aviation, we have them broken into amber and red, or yellow and red, where a yellow warning is a precaution. It's something to be aware of. Obviously, in this example right here, there's a lot of yellow. So you want to look into what happened. Was that, operating on the edge of where the aircraft is safe, or is that a degraded system that we actually should put in for some preventative maintenance? So making sure that these alerts are visible, not just when the pilot is flying, but also after the flight. The worst thing is, having to question, did I see a warning? I'm not sure. I think it was this one, and not having the answer, but really using the technology available within the app and how the aircraft communicates to the app to bring that to the pilot as soon as possible. It makes it so it's easier for us to maintain the aircraft, and also easier for pilots to improve their proficiency. And now we get to the training, which is one of the things that I think is so critical about what we do every day, and so important in every role here at Pivotal. We have a customer quote that says, "You practice in the simulator until you go up and hover. The first time that you have your first safe landing, you really get that you're doing this, and you really get that how good the simulator is." So this kind of brings me back to the title of the presentation here today, is From Sims to Sky. So the first time that you experience this aircraft as a pilot, both an RPIC pilot and as an in-cockpit crewed pilot, is through the simulator. So not only have we been designing an aircraft for the last 10 years, but we've also been designing a simulator to go with it. Because with a simple aircraft where you can only have a single person on board, how do you make sure that that very first flight, which is ultimately going to be a solo, is going to be successful? So how we've attacked that here at Pivotal is to make the simulator as realistic to aircraft as possible. And it rotates backwards and forwards as a full VR environment, and actually is programmed to be the same site that you're going to be flying for your training. So we can easily change the different sites, and so that you can practice the exact pattern that you're going to be practicing when you do your first real flights in the simulator, in your controlled environment with a teacher right beside you. Another pillar that was important to us and continues to be important to us is leaning on traditional aviation wherever possible. So all of our flight instructors are trained CFIs. So they're certified flight instructors from the FAA. And that means they can take all that they've learned through putting traditional fixed wing pilots or rotor wing pilots through traditional practices within the FAA to simplified flight controls and to aircraft like Blackfly and Helix. Because ultimately, a lot of the components within a private pilot's license are not required and not really relevant for an aircraft like this. We have a very simple aircraft. The fact that it goes from hover to cruise, that it uses batteries and electric technology, that it has a single joystick and a view screen. These are things that we Pivotal need to train the pilot. So it's important for us to have a comprehensive training program that is focused on traditional aviation and uses the best practice of having an ACS standard for every, and a performance-based standard for every course of the training lectures, but also to make sure that we're focusing on what we know. We've been designing this technology for the last 10 years. We know what's intuitive. We know where people struggle to learn. We know what systems can degrade. So we put students through typically 1 to 3 days of just flying in the aircraft under nominal conditions in the simulator, and then somewhere between 3 to however many you need days to fly in the aircraft in the simulator with emergency scenarios. So with wind, with high temperatures, with a degraded system. We've never had an aircraft flight where the GPS fails during flight, but it's physically possible. And there are places in the US where it might be more likely than others. So we want pilots to experience that in the simulators before they ever take to the skies. And that's something that we can do in a really controlled way. The actual very first flight that you do is incredible. It's just a straight up and down. So we make sure that you get all of the potential nerves out by taking it really slowly. Now, that first flight is the straight up and down, but over the course of 8 flights that you can complete in a day, you can be fully qualified to be able to fly. Using a check ride similar to traditional aviation is how you get qualified. And then it's important for Pivotal to continue to make sure that we're building in proficiency metrics within every course, the skill that you need to show, so that that check ride is ultimately saying you're good to go, and not just that you can do a pattern one time. So hopefully through the course of this presentation, you've got to hear a little bit about what it's like to build early stage technology with the future of the production model in mind. Also taking steps to leverage data and training and simplified flight controls to be able to analyze that aircraft and speed up the manufacturing and the design over time, and also keep the aircraft and the people safe. So I'd love to open it up for some questions if there are any questions for this presentation. And really thank you, and thank you to GoAERO for having me for this series.
Kristina, thank you so much. Actually, just really cool to see everything that you guys have been up to and what you've developed, and sort of seeing the flight simulations and actual flight is just pretty incredible. And I'm sure incredibly inspiring to all of the teams as well. As a reminder, please use the Q&A function in the Zoom to post any questions that you might have. And I might just sort of start, Kristina, with, you know, our teams are all sort of at different stages, but many of them at the very, very early stages of design and development. And I wonder, given now that you're 10 years in, looking back at sort of your very, very early stages, are there some pieces or some lessons or some pieces of advice that you might offer to the teams, things that you really sort of learned along in those very, very early days that might be useful and helpful to our teams?
Absolutely. So one of the things that sticks out to me the most is to remain focused. So one of the things that helped Pivotal and Blackfly really develop was that Marcus in 2014 had the Pivotal Helix airframe architecture applications in mind. So understanding that there is a need in the environment, which obviously everyone who's working in GoAERO, there's a dramatic need that we're going to fill. So not just technology for the sake of technology, and focusing on a kind of a path to be able to get there that is working in an iterative way as much as possible. Many of the companies are going to need to pivot, and that happens in that early first kind of 3 years where you're building a technology. Maybe you have one airframe, so if you want to do a whole new wing design, you can pivot over to a different wing design because you just have that one aircraft. But I think what was really critical for us was understanding that the first thing had to be propulsion systems. It had to be, can we have enough power? Can we have enough, the battery and propulsion system? So it didn't matter if the rest of the aircraft was kind of made out of bamboo sticks. We needed to know that that system could lift the payload that we needed to lift. Then next it became the duration of flight. We knew we needed to fly at least 10 miles back then. And so designing the airframe so it can fly at least 10 miles, really dirty airframe and stuff, but the configuration. So really coming up with a roadmap within the company of what are the hardest things and the most important things to be able to solve. And for ours, that was propulsion, that was duration, that was the ability to both hover and cruise and transition. So that was the kind of the third milestone, is to be able to get through those three, and then focus on reliability and optimization of airframe and systems. So, and then as I said in the presentation, really leveraging data as much as you can, because if you have a structured approach, then it means that with this data that we have, we're either going to continue forward or we identified a risk and we're going to pivot. So I'd say that that strategy worked really well for us and allowed us to move quickly and rapidly to design the Blackfly V1 aircraft. That was a strutted design. It had no cockpit, but was one that we could iterate very quickly on. And we could prove some of the fundamentals of the technology before we focused on things like fairings or the exact aerodynamic airframe to be able to, because we knew that those things were feasible. So focusing on the harder things first.
So there's a question from the audience. Early on, the quarter scale model of Blackfly had an interesting pitch characteristic. Could the simulator model the tuck maneuver? And could the sim be used to find solutions to this idiosyncrasy?
I'm not sure what the question is asking with respect to the tuck maneuver. That's not one that I'm familiar with. We did have a quarter scale model of the aircraft that we flew. We built about 15 of them. And because the power to weight ratio was quite different on that from the actual airframe, the aerodynamics were quite different. Now, because the ultimate design was going to be large, it didn't have to be exactly the same in simulation. But that's a very good question. And I think, it would be something to figure out with your team of, is it important to fully model the quarter scale? Is that going to get you a better full scale model and better understand the aerodynamics of the system? Or is it more important just to understand the areas of the aerodynamics that are similar and how the aircraft flight controls work? But that's a very good question. And I think it's one for that team to try to decide is how do you bound how close to 100% accurate you need to be at each stage of the development process.
And Rob, if you want to clarify the tuck maneuver, perhaps we can sort of add some more insight there. Another question is, since the goal of GoAERO is to have users with limited to no previous flight experience, how much more simplification can be applied to the flight experience? How likely is it that you could take perhaps a professional paramedic and give them the ability to operate a platform such as this?
That is a phenomenal question. So how hard is it to train someone without a background in aviation to be able to fly? Is like one question that I heard there. And what can you do to make it easier or simpler for them to be able to fly? So thankfully, paramedics are already extremely trained individuals. So they're the genre of people who they have gone through training, they understand what it means to learn, they understand what it means to do check rides and check flights and things in the paramedic space. And that's enormously transferable to flying aircraft. It's all hazard and risk analysis. It's understanding your skills, your proficiency at a time. A paramedic needs to say, I can't do surgery, I'm not a surgeon. They need to know the bounds of where their skills and proficiencies are. And that's very similar to aviation. So we've actually found training paramedics who have no aviation experience to be really easy, provided that you have a great training program. So you really need to understand the aircraft and the vehicle. Now, our vehicle is quite easy to fly. It's a simplified flight controls. It's quite intuitive, and we have a rigorous set of tests within the simulator to put everyone through. So I really think that paramedics are great people to train. Paramedics, firefighters, people who've gone through extensive trainings previously, whether it's in a different domain from aviation, the skills are still very transferable. Now, how to make it easier for people like paramedics to learn how to fly? Well, if you think about the paramedic, when they're going to fly this vehicle, whether it's crewed or uncrewed, they're focused on the mission that they are trying to help somebody. So they can't be focused 100% on flying and checking all the airspeed sensors and like doing all these things. You need to have the aircraft reporting to them so that they can focus on what they're doing best. Because this is probably a high stress situation where they're being dispatched and every second counts. So we need to make sure that everything is as intuitive as possible. Some of the things that we've learned here at Pivotal, for example, are you can say on the flight deck that a airspeed sensor is inconsistent. And that's kind of engineering lingo that makes sense to all of us engineers. But to the pilot at the time, what they're looking for is, why do they care? What do they do from that? So don't make them search for that answer. Give them the information on that flight deck so that they know what that means. It could say, landing compromised, proceed to alternate landing site. It could say airspeed compromised, transition to a different mode, or be able to include that information for the pilot or not show it at all if it's not a factor for flight. So really simplifying how the aircraft is communicating with the pilot is a really key element. Also making sure that they have the ability to be able to practice and maintain their proficiency, whether that's from flying routinely, so they're in muscle memory. With those of us that drive cars pretty frequently, we're pretty comfortable driving a car. But as soon as you get to the other side of the road and you change something, it becomes a little bit harder when you travel to other countries. So we want to eliminate that, okay, you haven't done this in a while or there's something new about it. So really triggering so that every flight path is done the same. There's the same pre-flight, there's the same flying characteristics, and then there's the same landing post-flight characteristics, making it really repeatable is the second thing that I think will make it easier for paramedics to be able to learn. And then trying to think of if there's anything else. For the paramedics specifically, they really need to know where their equipment is going to be because every second counts. So they need to be able to quickly identify where are they going, what do they need with them, how are they going to get there, and what are they going to do once they get there. So really having the logistics pre-planned as much as possible alleviates the number of decisions that that paramedic needs to make along the way and makes that a safer and more positive experience for them.
Great. So just stepping back quickly on the tuck maneuver, Rob just wanted to clarify that the vehicle would do a forward roll, pitching down dramatically, sometimes doing a full 360-degree in the pitch direction. Modeling and solving this in a simulator would be very beneficial.
Well, I appreciate that that Rob, you think that that's really beneficial. I would love to see that as an engineer. The more that we can make our simulations accurate to accurate to reality, the more that we can learn from them. So, you know, if I'm trying to kind of understand where you're coming from, and I'm going to make some assumptions here, I think what you're saying may be somewhere along the lines of, well, if you understand the power to weight ratio of a vehicle, and you want to be able to do a specific maneuver, if you can model that maneuver 100% in simulation, that'll give you a stronger tool to be able to compare your real experimental data with the analytical data. Now for us, we didn't have a maneuver of a forward 360 roll that we need to qualify on the ultimate total airframe design. Part 103 restricts the aircraft from aerobatics. So we do have pitch and bank limits on the vehicle that prohibit you from even attempting to do something like a forward roll. But for small scale models, if that is your mission, it would be really valuable, as you're saying, to be able to model that in simulation.
Great. How much more range performance do you think technology will allow you to get from a vehicle while still conforming to Part 103?
That's a great question. We have been looking at battery technology since I joined the company in 2015. I've gotten pretty excited a couple of times about new battery technologies or companies in the space. There's been small iterative improvements over the last 10 years. I do believe that the range will increase of the vehicle, and we're testing technology today that is highly likely to do that, although we're not ready to disclose exactly how far. We're looking to partner with battery companies and technology companies to be able to push that as far as we can, because ultimately the weight of the vehicle is restricted within Part 103. So the more performance we can get out of the batteries, the further you can fly, and the better, the more missions you'll be able to fly as well.
Were hybrid power systems ever considered for your vehicle to extend that range, or were they just too heavy for Part 103?
So absolutely they were considered hybrid systems, and absolutely they were too heavy for Part 103. So you hit it with both of your comments. Now, many different types of future aircraft won't be restricted by Part 103, and the hybrid system is enormously valuable to be able to increase that range. It makes sense from a technology perspective, and that's why a lot of the companies are going in that direction.
Right. I think that's the questions we have for now. Kristina, thank you so much. I wonder if there's any final pieces of advice that you might offer to our teams, as they're currently, if you may not know, they're currently in the stage of developing their prototypes for stage 2, which need to be at 35% subscale at minimum, if not at full scale. So that's currently where the teams are now, and that deadline is coming up at the end of September. If there's any final pieces of advice that you might want to offer to the teams, I'm sure they would appreciate it.
Okay, 2 pieces of advice come to mind for the teams in this stage of development, and consider failures as successes. So there were many times in those early stages of the company where we failed and a test didn't go as planned. A design wasn't able to have the performance that we needed it to, but that was ultimately information we needed to get early. If we were discovering that, 1 or 2 or 3 years down the line, we weren't in a as good of a place to pivot. So, try to fail early and consider those successes. Be transparent about the information that you have so that your team can collaboratively work together to fix them. And don't be afraid to take on the unknown. It's quite easy to just copy what somebody else has done and say it worked for them. Let's see if it can work for us. And that's a good way to bring in known good technology, but also question that and be curious and say, is there a way that we could make this 1% more efficient, or have 1% more energy over here, or do it a little bit differently and just celebrate that, because that is ultimately how you create new technology. And I really can't wait to see the designs that come out in September.
Thank you so much, Kristina. We really, really appreciate it. As a reminder to the teams, we are currently offering virtual design reviews to all those teams that have completed their stage 2 paperwork. So we encourage you to go to the website to find those details so that you can have this opportunity to get feedback from experts. Thank you so much, Kristina. We very much appreciate your time, and we look forward to sharing the designs with you as they come along.
Thank you for having me. Have a great day.